back. In this video, we're going to try to sketch the graph of a rational function by using all the tools that we developed in this chapter, including the first derivative test, second derivative test, test for increasing or decreasing of a function, or test for concave downward or upward. So in other words, we're going to bring all the pieces together today to sketch the graph of this function. And we did a similar thing in pre-calculus session that we were point plotting the graphs of functions, but the functions that we're dealing with here are much more complicated. These are rational functions. Point plotting may not be enough because we don't know if this graph has vertical or horizontal asymptotes, or we don't really know the behavior of increasing, decreasing, or concave upward, downward. So now that's why I said, like, we're going to bring all the pieces together. And here's a perfect guidelines for analyzing the graph of a function. So first, we're going to look at the domain and range of the function, okay? And we're going to determine the intercepts, asymptotes, and symmetry of the graph. So these two items are very similar to what we did in the pre-calculus session. So what's new here is the existence of maybe horizontal asymptotes, vertical asymptotes, or slanted asymptotes. You have a slanted line, and the graph of the function goes to infinity or minus infinity along the slanted line. And once we are done with those, we're going to find f prime and f double prime. In other words, we're going to look at the first and second derivative tests, as well as the test for increasing, decreasing, or concave upward and downward. And eventually, we're going to bring everything together to see if the function has relative extrema or points of inflection. So let's hit the road. All right, we have a lot of things to check. Let's start with the domain first. Both functions are well defined. And when we have a rational function, remember from calculus that when we check the domain of this, we only check if there's any x, making the bottom of the rational function 0 plus x squared is always bigger than 0. It can never ever be 0. So we can go ahead and then conclude that the domain is minus infinity and infinity. So you have x squared at the top, you have x squared at the bottom, but it's 3 more than the top. You're always dividing the top by a number greater than that. So that in turn is going to give you something in between 0 and 1. So the range is 0 and 1. How about the intercepts? The y-intercept is pretty easy to find because all you're going to do here is to plug in 0 for x. Okay, 0 for x, and then check for the function value at 0. So 0 squared divided by 0 squared plus 3 is essentially 0. Solve for it. Okay. Well, this is a rational expression, so let's make the right-hand side a rational expression by putting a hypothetical 1. So 0 divided by 1, and do the cross product. Essentially, you get x squared equals 0. That implies x equals 0. And when x equals 0, we know from the previous step that y equals 0. So in other words, x-intercept and y-intercept coincide, okay? The next item in the checklist is asymptotes. We have different types of asymptotes. The domain is like the whole real axis minus infinity and infinity. So there's no way to get a vertical asymptote for that purpose. Horizontal asymptotes, well, we just did it in the previous chapter. We should look at two limits, in fact. One is the limit of the function at infinity. And the other one is the limit of the function at minus infinity. Just if you have a rational function to start with, like in these two cases, all you're going to do is looking at the degrees of the top and the bottom. Well, we have x squared here, the degree is 2, and we have x squared plus 3, the degree is as well 2. So the fact says that the limit behavior of the function at infinity is the ratio of the leading coefficients of the highest degree terms. Okay, well, the coefficient of x squared is 1. It's 1 times x squared. And for this one as well, 1 times x squared. So 1 over 1, which is 1, is the limit behavior. And the same limit is valid, same limit value is valid for this kind of limit, because it doesn't matter if x goes to infinity or minus infinity for this problem, because eventually you square minus infinity, so it becomes infinity, so it doesn't matter. So this limit as well is going to be 1. We have a horizontal asymptote, which is equal to y equals 1. All right, the next item in the list is to check for symmetries. All right, here is how we check for the symmetries. For the x-axis symmetry, we replace x by x and y by negative y. And for y-axis symmetry, we replace x by minus x, y by y. And for the origin, we replace x by minus x, y by minus y in the description of the function to see if you can get the same expression after these changes. Let's do two of them. So I'm going to replace x by x, y by minus y. Here we go. X is replaced by x, so you have the same x squared plus 3 popping in the right-hand side. But the left-hand side is minus y. Well, you can easily see from here that these two functions are not the same. There's no symmetry about x-axis. Whereas if you look at the y-axis symmetry, so you still have y on the left, that's preserved. On the right, you have minus x quantity squared, and another minus x quantity squared in the bottom. In turn, the right-hand side is essentially the same as the right-hand side here. So we can go ahead and we put a check mark here that we have the y-axis symmetry. And you can go ahead and check that minus y is equal to just x squared over x squared plus 3. That's not the same as the given function. We have a symmetry about y-axis. Items number 1 and number 2 are all check marked. Okay, good. So now let's move on to the last step. Well, here we go. Let's look at y prime. Well, we have a quotient, x squared over x squared plus 3. Why don't we go ahead and use the quotient rule? Here's the application of the quotient rule. So you have the prime of the top times bottom, and minus top times the prime of the bottom, all divided by bottom square. There we go. So x squared has the derivative 2x, and this term is just kept forward. And then x squared is kept forward here, and the derivative of x squared plus 3 is just 2x. And all divided by x squared plus 3 squared. So let's simplify the top by expanding it out all the way. Here we go. So 2x cubed cancels this 2x cubed, then in turn, right? So this was sort of like a nice workout for you to warm up for y double prime. Because y double prime is going to be a little bit more complicated than this, but you will still apply the quotient rule. So I'm just going to write down what y double prime is, and at this moment, you can go ahead and then just write y double prime and try to match it with my y double prime in the next portion of the video. All right, after this workout, you should have had this kind of expression. I kept the expression of y prime here. I'm sure that by now you burnt a lot of calories for this. All right, so what we're going to do is to look at the critical points and inflection points. So critical points for y prime and inflection points for y double prime. And critical points and inflection points are very similar in terms of how we find them. We're going to look for x's that either make y prime 0 or undefined. And the same way here, we're going to find x's that make either y double prime 0 or undefined. Both of these guys are rational expressions, and since there's no x that makes the bottom 0, so there's no x, in other words, that make these functions undefined, so we can go ahead and conclude that we don't have the doesn't exist type inflection or critical points. So in the second case, we're going to set these equations to 0 and try to solve them. Well, setting the rational expression to 0 means like setting the top to 0, right? Because you can also put a 1 here or 1 here. Do the cross product, you will just see that you're actually setting the tops of the rational expression 0. Well, the good news is that from here, I have x equals plus or minus 1. So these are two inflection points. And from here, I have x equals 0, which essentially means that I have one critical point, which is x equals 0. So here are the inflection points, negative 1 and 1, and I have my critical point 0 listed here. So you should probably list numbers from the smallest to the greatest. We were picking sample points from each subinterval, and we were trying to evaluate f prime and f double prime for those sample points. If you have your TI-84 with you, why don't you go ahead and look at f prime at minus 2 and f double prime at minus 2 and f prime at negative 1/2 and f double prime at negative 1/2. And same as for, do it for 1/2 and 2 as well for each function f prime and f double prime. And try to convince yourself that for this one you have minus, minus, plus, plus. And for this one you get minus, plus, plus, minus. And from the increasing decreasing test, we can immediately conclude that the function f has to be decreasing here because f prime has the sign negative here. And here on this subinterval as well, f is decreasing. And f is increasing on this subinterval, and f is as well increasing on this subinterval. And let's look at the signs for f double prime here. Since the sign is negative, so f will be concave downward here, and f will be concave upward because it's a plus sign here, and plus sign here as well. And here f is a minus sign, and f will be concave downward. So the last line in the row is in fact bringing all the information together to determine the exact shape of the function. So for example, you have concave downward here for a decreasing function. Well, concave downward is something like this. It has two pieces, right? So one is the increasing piece, the other one is the decreasing piece. When I say concave down, it doesn't tell which one to use unless I use also this data here, this row. It says decreasing concave down, then I'm going to go ahead and get this part here. Here we go. It's concave upward. Here we go. I have two pieces of concave upward, but I'm going to look at the decreasing concave upward. Here we go. I have the decreasing concave upward because the other side is increasing, which is in fact the third column here. We have concave upward together with the increasing part. As you see, I got this part of the graph. Here we go. I get this part of the graph. And concave downward, which is increasing here for the last column. And I'm going to get this piece here. In fact, I got all four pieces here all together. And then we can use the test for the relative extrema. All right, we check what's going on at the inflection point. So it's decreasing. All right, still concave downward. The concavity changes at this point, but the decreasing behavior doesn't change. So that's not going to produce any relative minimum or maximum behavior. However, for this point here, which is a critical point, 0, right? So the function keeps decreasing. It's concave upward. It's still upward, but it turns back up. So that means the graph of the function is going to be flat at this point. It's going to make a D and then turn back up, right? So then we should have a relative minimum over there. For this inflection point, as you see, the function is increasing all the way across the inflection point. Even though the concavity changes, we don't have any relative extrema. So here the conclusion is that we have only one point, which is our critical point. In fact, that produces a relative minimum point. So now it's the time for verifying our analysis by graphing the function. Go ahead and graph the function x squared over x squared plus 9. I graphed it over the course of like x min to be -4, x max to be 4. So you can go ahead and then adjust your calculator accordingly. But remember that we had a horizontal asymptote y equals 1, so I had to sort of like list that in. And I have my critical point 0 here, inflection point here, another inflection point here. And just matching with the table, downward, upward, upward and downward behavior. Here we go. We just observe all of them, in fact, here. Concave downward and upward all the way between two inflection points, and then concave downward here. There's only one relative minimum value happening at x equals 0. The function values approach 1 as x approaches infinity or minus infinity. So this video was long. I'm sorry about that because we had to bring all the pieces together. We had to sort of like verify our findings by matching the table with the graph, and this ends the video. Thanks for watching. I'll see you in another video. Bye.